Yeah, so let me start. Thank you very much for the invitation to speak here about attosecond science. Thank you very much for the kind introduction, and also thank you very much for already explaining what an attosecond is. And so the attosecond pulses that I'm going to be talking about here today are pulses with a duration of about 10 to the power minus 16 seconds, so not quite 1 attosecond, but about 100 attoseconds. And what I want to talk to you about is how we can begin to use these pulses to learn about electronic motion in real time. In the sense that our primary interest is going to be to monitor the motions of electrons in time. Motions of atoms in time for us is too slow. They're too sluggish. They don't move on these timescales. So I'm particularly going to be talking about electrons, and I want to start with one of the first moments in time, or at least a very crucial moment in time, when people started thinking about electrons. So basically, I'm starting my talk about 100 years ago, almost exactly 100 years ago, when Niels Bohr, you see the picture there, was thinking about this measured spectrum of solar light that reaches the Earth. And so basically you see, as we all know, I mean, solar light has all the colors of the rainbow, but you see that some colors are conspicuously missing from the spectrum. You know, some wavelengths don't arrive on Earth. And Bohr thought long and hard of it, and of course then came with the very important quantum hypothesis, where he said that, where he hypothesized that in a hydrogen atom, the absorption that takes place is due to hydrogen, that in hydrogen, the atom can have only very distinct electronic states, and absorption of light, so missing colors, corresponds to a situation where an atom makes a transition from one particular state to another. And then he also came up with a very clever criteria for what these states then actually were. And basically, he associated a wavelength with the electron that circles the proton in the hydrogen atom. And then basically when the length of an orbit matches an integral number of wavelengths, then that leads to an allowed state. And if the wavelength does not match, then there's basically no state at that particular area. And so that is basically the major breakthrough that Bohr came to in 1913, and that basically led to this picture of thinking about atoms in terms of a nucleus with electrons that are orbiting around the nucleus in the sense of a kind of planetary system. This picture that you see in many textbooks, and that corresponds to the way that many people still think about atoms, is very wrong, and is really fatally flawed. And the way that this picture is fatally flawed is that it leads to a description of the electrons in our atom that, at a certain time, have a well-defined momentum, are at a well-defined position, and basically violates the theories that followed the work of Bohr in the next 10, 15 years, basically violated the theory of quantum mechanics as it was defined by people like Schrödinger, people like Werner Heisenberg. By the way, this is the real Heisenberg, not the well-known TV series character that we saw more recently. So basically what Schrödinger and Heisenberg taught us is that we have to think very differently about atoms. We have to think very differently about what we can know about the electrons in our atoms. And rather than little planets that are orbiting around the center of the atom, the electrons in, for example, again, the hydrogen atom look like this. So basically what Schrödinger and Heisenberg told us is that all that we can know about the electrons that we have in our atoms are probability distributions, so not exactly where they are at a given point in time, but basically the probability to find the electron at a certain place with a certain momentum. And so this basically leads to the concept of the wave function, which of course we've all heard of, and many of us, I think, in this audience have also worked with wave functions. We always use wave functions to make predictions for how a certain atomic or molecular experiment can behave. But we've actually never really seen these wave functions. And typically also we would argue that we can't. And that is to say until recently. So now we really jump to the present day. Here is a person that you probably have not heard of before. This is Aneta Stodolna, who got her PhD in my group 2 years ago. And she did an experiment here, which I'm not really going to explain to you in detail, where she actually imaged the probability distributions that we have in a hydrogen atom. And so basically here you see the pictures that follow from the quantum mechanical theory that Schrödinger and Heisenberg put forward, let's say in the late 20s of the last century. So basically you see that we've started with a planetary description of atoms, the Bohr model, and now through quantum theory, the work of Schrödinger, Heisenberg, we've gotten quite far away from this. What my talk is going to be about, and what I want to present you about attosecond science, is how it allows us to develop pictures, how it allows us to develop movies of processes in atoms and molecules that to some extent take us back to the planetary picture. That there is some sense to it after all. So let's, one more time, look at the Bohr model, or basically what underlies the Bohr model. And so that in the hydrogen atom, we say that we have a number of distinct electronic levels, and light is absorbed, or light can be emitted, when we make a transition from one level to another. Now, one of the beauties of quantum mechanics is that if we shine light with many, many different colors onto the atom, that actually absorption into several excited levels of the atom can occur simultaneously. And so not just a transition from one level to the next, but a transition from one level to multiple excited levels, multiple possibilities that there are. And that is basically when the excited state that we then form begins to acquire a little bit particle-like behavior. In the sense that's related to the pictures that I showed you a moment ago, with each of these excited states we can associate a kind of wave. And if we have all these colors available to do the excitation simultaneously, then what we are forming is actually the superposition of all of these slightly different waves. Now, and that basically looks then like this. And so here, okay, this is not an atomic model. I've just taken a few different waves with slightly different wavelengths and superimposed them. And you see, if I take enough of these waves, then by means of constructive interference, it piles up in one area, and by means of destructive interference, it goes nearly to zero everywhere else. So basically, I'm creating a concentration of the probability to find a particle in a certain range, which is a bit particle-like. Not exactly a particle, but particle-like. And so how this would actually look in a hydrogen atom is shown in this little calculated movie. And so here, initially, you see a quite well-defined object that is circling around the proton, almost as if we have the planetary model of Bohr. Of course, at later times, you see this thing breaking up. That is where the quantum mechanical features of the model start to become visible. Now, this behavior, so these time dependencies of the probability distributions that our electrons have in atoms, molecules, whatever material we are interested in, this is what we would like to see in attosecond science. This is what we would like to get at. We would like to see almost directly. So for that, I'm going to now tell you and explain to you how we use lasers, especially short pulse lasers, to make, in a sense, movies, to record time-dependent processes. And again, when it comes to our inspiration for this approach, we go back a long time in history. In fact, we go even a little bit longer back. We go back to 1886, and we go back to the work of Edward Muybridge, who was a photographer at the time and who developed the technique of stop-motion photography in order to answer what at that time was a crucial scientific question, and that basically was the question whether during its galloping, a galloping horse ever comes off the ground with all of its four legs at the same time. So a lot of debate about that. People could not answer it. So Muybridge, he answered the question by doing the equivalent of what today we would call a pump-probe experiment. In a sense, there was an initiation of the galloping of the horse, and then at various moments during its galloping, he took snapshots, and then these snapshots we can all put together to make a kind of movie. And so here you see some of his snapshots recorded on a racetrack near Stanford University. And if we put all these together, we see, what now would be a common movie of the galloping horse. And of course, we see very clearly that it comes off the ground with all of its legs. Like I said, this is what we would call today a pump-probe experiment. There is an event that's what we typically call our pump event, that initiates the galloping of the horse. And then at a variable time delay, there is a probe, a snapshot is made of the instantaneous shape, the instantaneous situation that we have. Now, obviously, we don't use these techniques for galloping horses. We use these techniques for much faster processes. In the last few decades, a lot for atomic motion. Now, with these attosecond techniques, we're beginning to do this even for electronic motion. And so let me show you one example. This is then for an atomic motion, what such a typical pump probe experiment might look like. So this is a pump probe experiment in the hydrogen molecule. So H2, we have two protons held together by two electrons that form a chemical bond. What we do in the experiment is that we excite the neutral hydrogen molecule with a pump laser, that is later actually going to be an attosecond laser, as we will see, that ionizes the molecule, so it strips one electron that flies away, and at the same time it starts a vibration of the H2 plus ion that is left behind. In a sense, molecules, and in this case this H2 plus ion, we can basically think of as a couple of atoms that are held together by a kind of spring. This chemical bond acts as a kind of spring. And so this process forms the H2 plus away from the equilibrium position of the spring. And it basically means that after this pump excitation event, the spring is going to vibrate a little bit. And the way that we see that in the experiment is by means of our probe laser. So the probe laser is a laser that we bring in at a variable time. And this is a laser that dissociates the H2 plus. So basically it fragments it so that afterwards we have an H plus and a neutral H atom, and we detect the H plus. Now, this probing process is especially easy if the spring is very far extended. And that you can see from the diagram that I show you there, in the sense that just as we did it in the atoms, I show you here the energy levels that we have in a molecule, except of course that in a molecule, all of these energy levels depend on the internuclear distance. And we also have to consider what is the energy as a function of the internuclear distance. And then what I can see is that if the atoms are far apart from each other, so if the spring is really extended, I need only a little bit of energy to break the bond. That's basically where the arrow is drawn here. On the other hand, if the spring is contracted, I would need many, many photons from the probe laser. That is something that I don't see. And so basically here in this measurement, we measure the H plus ions that are formed in the dissociation. And whenever we see a bright red spot, that basically means that the spring is extended. The atoms are far apart from each other. And we see that this comes and goes and comes and goes. We see the molecule vibrating. And so this is a typical example of a pump probe experiment. Now, pump probe experiments of this kind have meanwhile been done for decades. I mean, basically, as soon as lasers were developed, in particular as soon as short pulse lasers were developed, people have started doing these types of experiments as applications of the lasers. And so here you see a diagram which I've taken from the Nobel lecture of Ahmed Zewail, who in 1999 got the Nobel Prize for this type of experiment carried out in the femtosecond domain. And so basically, Ahmed Zewail, he developed the field of femtochemistry and got the Nobel Prize for it. And basically what you can see from this diagram, okay, there's many things that I'm not going to explain what they are, but basically what you can see from this diagram is that these are techniques that find application in a wide range of research areas in physics, in chemistry, in biology. For many processes, it's very interesting to study them in such a time-resolved manner. What you can also see in this diagram is that in the year 2000, the diagram more or less stops at 10 minus 15 seconds. It stops at, time resolution of about 1 femtosecond. And that is with very good reason, because that is also those were more or less the shortest pulses that were available at that time. In a sense, the speed of a certain process that you can monitor is directly linked to the duration of the pulses that you can use in such a pump probe experiment. And it makes a lot of sense. If you make a photo with a camera of a fast-moving object, and then the shutter speed at some point is going to decide how fast the object can be before you get a fuzzy picture that doesn't tell you anything anymore. And so basically what you see from this graph is that around the year 2000, the duration of laser pulses that could be generated seemed to be hitting a dead end at something like 2 or 3 femtoseconds. There's one thing that I still want to point out about this diagram. I mean, you see here as a function of time how people were able to make shorter and shorter pulses, and it's basically through a range of techniques that were introduced. One very important one of these is mode locking. And I briefly want to draw attention to this in the sense that I think you've often heard about the wave-particle duality of electrons. We've already talked about a little bit. Likewise, there is the wave-particle duality of light. Sometimes we think of light as photons. Sometimes we think of light as waves. And if we want to understand how we make short laser pulses, we again have to think about light in terms of a wave. And we again can rationalize the duration of our laser pulse in terms of the way that we're adding many colors together. And basically the mode locking that was developed in the late 60s was essentially a method to do this in a very clean way and to make all the different colors that were present in a laser system, to make them all line up in a very nice way, to get the shortest pulse possible given the number of different colors that were available. And so I hope that you see that it's almost exactly the same picture that we need to have to describe localization of an electron by adding electronic states and localization of light in time, let's say, by adding up colors. It's the exact same picture. Okay, but like I said, dead end around 2000. And that dead end, we can actually understand a little bit by looking at this diagram. Now, this is a pretty full diagram. I'm certainly not going to explain all the things that are on there. But what you see here is basically the spectrum of light extending from the ultraviolet on the left to the mid-infrared on the right, with, of course, the visible range somewhere there in the middle. And all the things that connect to this wavelength scale are lasers that you can buy commercially or lasers that you can readily build in your laboratory. Now, so what you see is that lasers that you can readily build in the laboratory or that you can buy commercially, they run more or less from the ultraviolet, let's say around 300 nanometers, up to the near infrared, more or less 1 micron or even a little bit beyond. What we have to consider, going back to this picture of stacking up waves in order to concentrate light to a short pulse duration, is how long it actually takes for light in a particular wavelength range to oscillate once up and down. And so what is the duration of one wave in one particular wavelength range? Now, that's about 1 femtosecond at 300 nanometers, simply 300 nanometers divided by the speed of light. That's 2 femtoseconds at 600 nanometers. That's 3 femtoseconds at 900 nanometers. So in other words, all of these lasers that I can buy commercially are unsuitable for making attosecond pulses, are unsuitable for making pulses that are shorter than 1 femtosecond. Because if I want to make pulses that are shorter than 1 femtosecond, then I have to stack colors where the optical period is in this sub-femtosecond domain. And that is something that I cannot buy. And for that reason, also, you cannot buy attosecond lasers. If you want them, you have to build them yourself. Now, fortunately, a technique was found to do this. And that is the technique of high harmonic generation that I explain on this slide here. So in high harmonic generation, we take a near-infrared femtosecond laser. Typically, this is a laser around 800 nanometers, where you can buy lots and lots of commercial lasers. This is almost off the shelf. And we use this laser in an experiment where we focus the laser onto an atomic or molecular gas. Like I said, these lasers are quite standard, and as you also heard in Victor's talk, it's quite easy. In fact, we use much smaller lasers than Victor does. It's quite easy to focus such a laser to an intensity where it will ionize the gas that is at the focus. Now, when that happens, when an electron is pulled out of the atom or molecule, Then at some point we will consider our system ionized, and maybe when the electron is removed from the ion by a few nanometers. But of course at that time the electron is still very much in the laser focus. I mean, our laser focus typically will have a dimension of 20 to 100 micron, so 1,000 times more than the distance where we would consider our atom ionized. And that basically means that's slightly different, but related to how Victor also talked about it, that we're going to have an acceleration of the electron, the liberated electron, in the oscillatory electric field of the laser. The electron, the laser field pulls the electron away from the ion, but then of course it becomes relevant that it's an oscillatory electric field. So a little bit later, a femtosecond later or so, the laser can also drive the laser can drive the electron back towards the ion. Now, and then when this happens, we get a collision between the electron and the ion. And in this collision, there's a small but non-negligible probability that a recombination will take place, that the electron basically goes back to the original ground state from which we have removed it. Now, when that happens, we have to go somewhere with the energy that we've invested in our system. After all, we've ionized the atom. That has cost energy. We've taken energy from the laser to do this. Then we have accelerated the electron to what can be a quite high kinetic energy, a few hundred electron volts or so. Now, basically, that energy combined can then come available as photon energy. And so basically, we're using our atoms to bundle many photons from our mid-infrared laser, and by that way, we produce a photon in the exact wavelength region that we need for the attosecond pulse production. And so this picture, and the fact that we could make attosecond pulses this way, is particularly credited to the two people that you see here. Paul Corkum, who basically explained that this three-step picture, that this is really a proper way to think about the generation of the extreme ultraviolet light. And Ferenc Krauss, who subsequently was very, very successful at actually making the attosecond pulses this way. Here you see them in a prize ceremony. This is 2 years ago, where they got the King Faisal Prize in Saudi Arabia, which is often seen as a kind of precursor for the Nobel Prize, but that they are still waiting for. So harmonic generation is a process that produces the attosecond pulses for us. Now the question becomes, how do we know this? I mean, how do you actually know that this process produces an attosecond pulse? It's not so easy to measure, right? Because I mean, typically when you take a light detector that you connect to an oscilloscope or so, this might allow you to measure a pulse that's a nanosecond long, but not much shorter than that. These pulses are more than 1 million times shorter. And you can say, okay, I'm going to use a little bit more sophisticated apparatus. I'm going to use a so-called streak camera. I mean, here you see the principle of a streak camera. I mean, if I have a pulse, a light pulse that has a certain duration, and I use it to ionize a medium, again, a gas, or I shine it at a surface, then basically I can generate an electron pulse that will have the same time structure. That electron pulse I can accelerate towards a detector, and if I then do a clever trick that I along the path that I send the electrons through a capacitor where I ramp up the voltage as a function of time, then I will create a situation where the electrons that come first have little or no deflection as a result of this voltage, and electrons that come later will have a stronger deflection. And it basically means that they will hit my detector at a different position. Right? In that way, I can map the time structure in my electron pulse, which mimics the time structure in my photon pulse, my light pulse. I can map that into a spatial distribution on the detector. That is called a streak camera. It's a very popular measurement device for measuring short pulses. But again, it's not nearly good enough for what we need here. I mean, if you build a really good streak camera, you can get a time resolution of maybe a picosecond. Still, a factor 10,000 too long for what we need. So the trick that people have come up with is actually to use such a streak camera, but to use a laser to generate the streaking field. And so basically not a voltage ramp on capacitor plates, but basically use a co-propagating laser to provide the quickly changing electric field that leads to the streaking. And so here you see the principle of what is called the attosecond streak camera. And here you basically see how the field of the oscillatory electric field of a laser, and that's then simply going to be a replica of our 800 nanometer laser, how this can accelerate electrons that have been liberated, typically from a gas, by an attosecond pulse. And how the precise moment when this ionization process occurs maps, again, like in a street camera, onto a position where we can detect a photoelectron on the detector. And so here you see an actual measurement, where the attosecond pulse is scanned completely over the infrared streaking pulse. You, of course, immediately recognize what then the shape of the infrared streaking pulse was, and you map out the oscillations of this electric field. But on top of that, from this measurement, you can also extract the duration of the attosecond pulse. And in this particular case, that was then a duration of about 250 attoseconds. That's pretty typical for the pulses that we generate. And so that basically means that we have a new diagram where, in addition to where we were in 2000, we can now at this point, I mean, the current state of the art for the generation of attosecond pulses is the generation of 67 attosecond pulses. That's the shortest people have gotten so far. Now, that basically also means that this diagram can be extended, and that it doesn't stop at a femtosecond, but that now we have the attosecond pulses that allow us to look at electronic motion in real time. So, in the last few minutes of my talk, I'm going to give you one concrete example that's then from our own work, what we've done a few years ago. And in this example, I'm again going to return to the hydrogen molecule, where we already previously saw the vibration. And also the pump probe experiment that I will explain will be the same. It's the same setup that I've explained to you before. So we have an attosecond pulse that acts as the pump in the experiment, and it's going to be followed by a short IR pulse later on that is going to act as the probe. Again, I'm going to look at what we call a dissociative ionization. So the attosecond pulse is going to ionize the molecule, but moreover, the molecule is going to fall apart into two fragments, one neutral H atom and one H plus ion. Now, and that actually introduces a very interesting question into the experiment. I mean, we can think of this dissociation process as a ball that is rolling down a hill. So that basically means that the two atoms, they will fly off in opposite, they'll be accelerated, fly off in opposite direction. And now we can ask ourselves the question, where does the H go? Where does the H atom go? And where does the H plus go? And how does the molecule know how to pick? And so we initially have a bound H2 plus molecule with a very high potential energy, and now it falls apart into two fragments. One of them is charged, one of them is neutral, contains an electron. And how does the molecule know whether the neutral H atom is going to go to the right or is going to go to the left? Now, I'm first going to show you the experimental result that we got. And so what you see here is a plot where we have measured an asymmetry. I'll explain in a moment what that is, as a function of the kinetic energy of the H pluses in electron volt units, that's common, and as a function of the time delay between the attosecond pulse and when we are probing with the IR. So red in this curve means that the H plus is flying predominantly towards the left and that the H is flying towards the right. And blue in this curve means that the H plus is moving towards the right and that the neutral H atom is moving towards the left. And what you can see is that as we vary the time delay between the XUV and the IR, between the attosecond pulse and the moment that we make our observation, this preference is going back and forth. Sometimes the H plus flies towards the right, sometimes it flies towards the left. Now, this is an experiment that we have analyzed in great detail, and as it turns out, there are several mechanisms, several different mechanisms that explain the observations that we have here. But I just want to point out one of them that is particularly intriguing. I mean, this is a mechanism that we could prove to ourselves in essentially a second experiment that we did. That was a numerical experiment that was done to help us explain the laboratory experiment. And so here you see the Mare Nostrum Cathedral near Barcelona, which is no longer used as a cathedral, but which now hosts a supercomputer center. And there, the group of Fernando Martin and his co-workers from the University of Madrid have been doing calculations on this problem, and these computers that you see in this absolutely beautiful building have been cranking away for about a year to explain why does H plus fly to the right or why does it fly towards the left. Now, and like I said, one of the mechanisms, not the only one, but one of the mechanisms that they have found, I schematically show here. I'm not going to explain the picture on the left. That's the picture from the paper that explains it in a formal quantum mechanical sense. What I would like to explain to you in words, what the mechanism tells us about what these H plus ions and electrons, what they are doing together. So what you can see, the experiment starts with the attosecond pulse that ionizes the molecule. So it basically means that one electron is kicked out of the molecule and is sent on its way. After a variable time delay, that's what we choose, this electron that flies out interacts with the probe laser. This we can recognize in the calculation that it's this electron that does that. And remarkably, that interaction with the probe laser of the outgoing electron, the one that has left the molecule and the one that is flying away, decides where the bound electron goes. Whether the bound electron goes towards the right or goes towards the left. So that's something you should let sink in. So we have an electron that flies away, flies out the door, and on the other side of the door there's a laser that interacts with it, and that interaction ends up deciding whether here in this room we see the H plus flying towards the right or flying towards the left. Now, so that is a consequence of what people call quantum entanglement. And so we have a quantum system that we think of in two parts. We think we have an H2 plus and we have an electron that leaves, but it is of course truly one quantum system. And that basically means that observations that we make on the electron that has left the room can have consequences for the other half of the quantum system, the H2 plus part. Now, that of course brings us back to the starting days of quantum mechanics. The quantum entanglement was one of the things that upset Einstein the most about quantum mechanics, and really one of the reasons why that he could not accept the theory. But it is of course a concept for which, meanwhile, in addition to this experiment, there has been quite a bit of proof. I hope that I've been able to show you a little bit how this field of attosecond science has been developing, and also that it now allows us to look in a quite fundamental way at exciting scientific questions. And I thank you for your attention.